So this module deals with sequential circuit timing, and really the purpose of it is to do some timing analysis. So we have seen that flip-flops have parameters such as setup time and hold time, and we need to stabilize certain signals within an aperture to avoid any metastability. And specifically, this video actually deals with how do we do timing analysis for a circuit that has sequential parts. And really what we're interested in is what is the maximum frequency we can actually operate at. So as it turns out, that these timing constraints will affect the maximum frequency that the system can operate at. And of course, all things being the same, if I have the same system, exactly the same system, and I use two different clocks, the one that is faster or that utilizes a faster clock should produce more work within the same amount of time. Anyhow, let's see how these timing constraints actually affect that circuit or that clock frequency, and let's see how we can actually calculate it manually. So before we get started, I want to mention that the minute or when you want to do some timing analysis, you want to start by saying, okay, I need to figure out the different paths within my circuit. And there are different paths in the circuit. So some path, for example, in here, let's highlight it in green, actually starts with a flip-flop and ends with a flip-flop. Then this diagram in here, I'm showing you a really simple circuit and has all different paths. So a path that starts from a flip-flop to a flip-flop, I think the easiest one to see is the one that starts with Q1 and ends with Q2. So it starts with a flip-flop and ended up with a flip-flop. And as it turns out, that this circuit has a couple more that starts with a flip-flop and end with a flip-flop. For example, Q2 has some sort of a feedback to itself through this particular XOR. So that's another path. And also, as it turns out, that Q2 actually starts by itself and loops back through an AND gate to Q1. So it's different from the first one. The first one started with Q1, ended with Q2. The last one I showed you started with Q2 and ended with Q1. What I'm showing you here is there are different paths here, and we need to analyze them. We need to make sure that the timing constraint for this flip-flop and this flip-flop are not violated, whether the setup time or the hold time. And as it turns out, circuits usually have other paths as well. For example, sometimes it's from an input to a register, something like this one here, from A to Q1, or maybe something like from a register to an output, something like Q2 to Z. And lastly, you might see something that is actually from input to output, something like that. And frankly speaking, the input to output probably doesn't matter that much because there are no sequential circuit parts in here. Anyway, in my discussion in the following, I'll just focus on the register to register here, which starts with a flip-flop and ends with a flip-flop, because as it turns out that it's the most complicated one, and the other ones can be just treated as special cases of it. If you know how to deal with a circuit that has a couple of flip-flops and you're maintaining the setup time and the hold time for both flip-flop, it's easy to do one or the analysis for a path that only has one flip-flop. All right, so I will focus on this register to register. So we're going to see a circuit similar to that. This is a generic circuit or a generic path that starts from a flip-flop or a register and ends with another register. So R1 is here and R2 are both connected to the same exact clock, so they're within the same system. And they're cascaded, or they're actually the output of this first flip-flop is called Q1, is connected through what we call a combinational logic. This could be any combinational circuit, multiplexers, decoders, a bunch of gates, whatever you can think of. What I care about is just a combinational logic. There are no clocks involved in that part, and it outputs something in here, and that something will be connected to the second flip-flop in here. So this timing diagram shows me some important timing parameters in here. So what I have is the following. I have a clock in here, and it's showing me the positive edges in here and another positive edge in here. And of course, this is the clock period. That's what TC stands for. And as we know that after the active edge of the clock, Q1, which is the output of the first flip-flop, will change or will stabilize. Well, if it needs to change, it will change after a certain delay. And that delay, we called it clock to Q. And what we did is we had a couple of clock to Qs. We had one that is a contamination one, which is a fast change. We called it contamination in here. Okay, and then we had another one that is what we call the propagation. And in this diagram in here and the rest of the diagram, you're going to see whenever I use gray, it's usually a contamination delay. Whenever I use blue, it's usually a propagation delay. But anyway, going back to this timing diagram, what I have is Q1, which is the output of the first flip-flop or the first register in here. After a certain period of time, which is contamination clock to Q, it will change all the way to the propagation clock to Q. So within that range in here, it will change somewhere in between it. Like the earliest it will be here, the last it will be here. And of course, that Q1 is used as an input to the combinational logic here. And this combinational logic, regardless of what it has, it also has delays. Okay, so, and as it turns out that this logic might make that signal pass through maybe 3 or 4 logic gates, and might end up with like more logic gates, or like 100 logic gates. So it also have a range of delays. So this diagram in here is showing me that the output of the combinational logic block might change anywhere between here and here. So the earliest, so whenever you have like some sort of a signal coming in here, it will change Q1, and eventually will change D2, and D2 will change, it will take some time, and that time is actually the minimum or the contamination delay for the clock to Q for the first one, for the first flip-flop here, and then also the minimum delay or the contamination delay of the combination circuit in here. So you will have to wait from the clock at least this amount of time for that signal D2 to change, and you can wait all the way up to this amount in here, which is the propagation delay. It's actually the maximum delay at Q1 and the maximum delay for the combination logic for it to change in here. So D2 can change anywhere in between in here. The earliest is in this point, and the latest is in this point. What we do care about is the following. D2 is actually the input for register 2. And what I care about it is when the next active edge of the clock in here, I need to make sure that this signal here is stable so that it doesn't violate timing constraints, whether it's setup time or hold time for the second register. So everything we discussed so far is the first register generated Q1, and then the combination logic generated D2. Now I want to make sure that this D2 signal is stable within the aperture of R2. And as it turns out, that this timing analysis I'm about to do actually just make sure that if this is maintained, it will actually result in what's the maximum frequency, and you're going to see with an equation then the maximum frequency or the maximum period or the shortest period or the minimum period, actually clock period, will appear in that. Just one note before we actually get started into the setup time and the hold time is any type of analysis I'm doing right now doesn't worry about the logic or the functionality of the circuit. So this circuit in here, we don't know what the combination logic is, and we don't care about it. So technically I don't know what this circuit is doing. All I care about is it might be also a part of a circuit, and all I care about is that it starts with a flip-flop, it ends with a flip-flop. I just want to make sure that the timing constraints for this particular flip-flop are not violated. All right, so let's get started. We're going to do this analysis 2 parts. We're going to make sure first that the setup time constraint is actually held or it's not violated, meaning I want to make sure that this D2 is stable before the active edge of the clock for at least T setup. And we're going to go back in here, and it's exactly the same diagram that we just seen before. It's actually, but whenever we do a timing constraint, we usually think about the worst case scenario. And as it turns out, and as you'll see, like if you pause a little bit and think about it, you're going to see that really what we care about now is actually the propagation delay. So I'm just going to remove the contamination delay for now. So what we see is the following. The active edge of the clock happens in here. It will take the contamination or the propagation clock to Q for the first flip-flop in here. So that's the maximum actually in here. So it will change. That's what I care about, is actually the maximum amount of time it needs to actually change Q1. And I'm going to do the same thing for the combination logic here. So I'm going to wait for the maximum of the propagation. So what I'm going to call this is the propagation clock to Q. This one here, I'm just going to call it propagation delay. That's what PD stands for. Propagation delay of the combination logic. What I need to do is I need to make sure that this D2, which will take at the most, I will have to wait for this Q to change, and it will have to wait for this one to change. It will take at the most this amount of time to stabilize. I just want to make sure that it actually stays at the same time for T setup. So what this tells me is the following. That in order for you to make sure that it stabilizes around the setup time is actually you need this inequality. What does this inequality tells me? That you're going to have to add the T propagation to clock to Q plus the propagation delay for the combinational part plus the setup. You need to have that TC at least that amount. It has to be equal this number or this addition or more. And this will make sure that the time or the setup time is not violated. So the setup time constraint tells me that your clock period has to be at the minimum the sum of these in here. Well, that's interesting because we can actually use that TC if we care about the maximum frequency. All we have to do is we know that the F clock or the frequency for my system is 1 over TC, which is just 1 over that sum in here, which is that number. So this particular constraint or this particular setup time constraint inequality will give me the maximum frequency that this system will operate at. If you have multiple paths within your system, you're going to have to do this analysis for all the paths you find, and then your maximum frequency is the smallest number because the worst path have to be satisfied. Anyhow, let's discuss a little bit more about this circuit in here. Usually, the propagation to clock is actually depends on this particular flip-flop, and I'm assuming we're using the same registers of flip-flops. So, as a designer, you usually don't have any control over it. You look at the data sheet, and that's what you get. The same goes with the T setup. The setup time is also out of your control. So that leaves you a couple of things: either the propagation delay or the frequency. And I'm going to tell you from now, usually the frequency of the system frequency is decided maybe by some engineering manager, or maybe a customer wants to operate at a very specific frequency because they have certain, like you're designing a system for a certain customer and that customer told you, I want it to operate at 75 megahertz. You can't deviate from that. So really the only thing left for you is the propagation delay. So let's take a look again in here and see what is the propagation delay. Well, it's the propagation delay of this combinational circuit. So as it turns out, really what you have control over is that combinational circuit. You as a designer usually just have control over the combinational logic here. So I'm going to just rearrange the terms around that inequality. So this tells me that you have to have that TC. Let me just do this here. I think it has to be less than TC minus T propagation to clock to Q plus T setup. Okay, so this inequality here tells me, and I believe this is what we call a sequencing overhead. This is like a technical term for the sum because it depends on the flip-flops only. So this tells me that the propagation delay, which is the maximum delay you can get out of this particular combinational logic, is capped. So you can't have whatever, like you can't have an infinite number. It has to be within that. And another term that I want to throw at you right now, because we're going to see it in whatever CAD tool you use, usually you see something called slack, and the slack is actually this amount of time in here. So it tells you the amount of time that you have in here is that much, or basically TC is like the sum is actually the slack. And more specifically, I'm reading that definition in here. It is actually just a slack is the time left before violating a time constraint. And usually what I want you to associate with is negative slack is usually bad if you see it. So you don't want the negative slack, you want the positive slack. So you want more time. What I'm saying in here, if TC is longer, that's fine. But if TC is shorter, that will be a problem. If TC is shorter, that means you will be violating the setup time. All right, so the setup time constraint told me what's the maximum frequency I can operate at. Let's study the hold time constraint now. So again, we're going to do some timing analysis in here, and in this particular case, the worst case scenario is actually happened to be associated with the contamination clock to Q, or the contamination delays across the circuit. So what this shows me is Q1 will change after clock to Q, or contamination clock to Q, and I know that the combination of logic here will change at the minimum after what we call contamination delay for now. All right. So this is, or Q1 is the result of R1, and the D2 is the result of the combinational logic. And what I'm saying in here is, usually you will see that D2 in here, it will be stable at least for this amount of time before it actually starts changing. So from the active edge of the clock all the way to here, there will be no changes in D2. And that's here, that's what we see. So the next active edge of the clock, which is right here, you're going to see the R2 will see the same thing that you'll see in here. Remember, everything is periodic, everything is being repeated, the same thing. So D2 will be stable for this amount of time. What we really care about is this amount of time has to be more than the hold time. So this equation in here is telling me that the hold time has to be greater than the contamination clock to Q and the contamination delay. All right, so that's interesting. So the whole time constraint tells me that you need to make sure is the following. Again, you usually don't have any control over this, or that they're usually the sequencing overhead. Remember, this comes from the flip-flop itself. So the only thing you have access to is the contamination delay. And what this is telling me is the contamination delay has to be greater than or equal to the hold time minus T contamination to clock. So what do we get out of this? Well, let me just copy this guy in here, okay, so that we get to see them together. Okay, I'll just copy this. What I really care about is the following. what I'm showing in here is that combination logic, the one we saw in here. Okay, so that combination logic in here has two constraints. Its contamination delay, or basically the fastest delay it can actually have, has to be greater than a certain number, and its propagation delay, which is actually the maximum delay it can has to be less than a certain number. So it should be, so what I'm saying in here, it should be fast but not too fast. That's what it's telling me. So there's a range of numbers that is acceptable, so that you have the setup time and the hold time being not violated, so that they're actually maintained. And another thing, if you actually take a look at this equation, you'll see that TC never appears in it, or the clock period never appears in it. And as it turns out, the hold time does not affect the maximum frequency. It's only the setup time that affects that maximum frequency in here. So the maximum frequency usually is obtained by the setup time constraint. In general, a properly designed flip-flop, or a good flip-flop, will have the following feature. Its T-hold will be much less than its T contamination clock to Q. So let's discuss this very briefly, and we can see it from the equation in here, we can see it in here. So what I'm saying is, you see that T-hold in here? I'm gonna make sure that it's less than contamination to clock to Q. So what does that mean? Let's take it that way here. So if this number is much smaller than this number in here, and both of them are positive, remember we're talking about time. So this is a positive number and it's less than this positive number in here. So that means this number will be negative all the time. So T hold minus T contamination clock to U will be negative. And of course, we're talking about time. This is always positive. What does that mean? It means that no matter what TCD is, no matter what it is, even if it's 0, the hold time will not be violated. So if you see that the hold time is less than contamination to clock to Q, usually you don't have to worry about the hold time constraint. Again, take a look at the diagram. It makes sense. Like if the hold time is actually in here, really the contamination clock delay does not matter. So let's make sure that that 7474 we looked at was actually, or had that particular feature. And you can see that I believe the contamination clock to Q in here is actually 25 nanosecond, and the hold time in here is 5. So what we have is exactly that. We have this is at 5 nanosecond, this is 25 nanosecond. So it will be extremely difficult, if possible at all, to actually violate the hold time constraint for such a flip-flop. And more importantly, we have seen shift registers, or even the synchronizer, which is based on a shift register, utilizes this particular structure, which is, it's a structure that starts with a flip-flop and ends with a flip-flop. And of course, there's a combination logic. What type of combination logic? It's actually just a wire. There's actually no logic whatsoever. So technically, what we have is we have something that doesn't have any contamination delay. So unless you have the T-hold in here that is actually much smaller, or at least smaller than the contamination clock to Q, you will never be able to actually cascade flip-flops this way. So most of the flip-flops you're going to see in reality will have a hold time that is less than the contamination clock to Q. So the hold time will be much, much smaller. And sometimes you're going to see a lot of literature, they just consider it 0, that the hold time is just 0 and that's enough. Okay, and this way we can actually connect these flip-flops in a cascade order. So let's combine all these ideas together and do a timing analysis for the circuit in here. So in this circuit, I have a register in here and I have another register, and really what I have in between them in here is actually, this is the combination logic part. This is what we call the CL. All right, so what I've been given is the parameters for all the flip-flops. I've been given the contamination clock to Q, the propagation clock to Q, the hold time, and the setup time. You might see that the hold time is actually more or greater than the actual contamination clock to Q, and we've seen, or I mentioned that in reality flip-flops usually are designed not in this way, but we're doing it in this example just so that I can show you how some of the constraints will be violated. And each one of these logic gates, regardless of what it is, I'm telling you that it has a delay. The contamination delay is 25 picosecond, and it will, the propagation delay is 40 picosecond. So it can result in an output between 25 to 40 picoseconds. So let's do this analysis in here. So we're gonna first study the timing violations. I'm gonna study the setup time constraint and then the hold time constraint. So let's start with the setup time in here. So the setup time constraint, setup time. Okay. All right. So the setup time constraint, first we need to actually figure out what the equation was, and I'm just going to write it in here. It actually tells me that the clock or the period has to be greater than the propagation clock to Q from the flip-flop, and then the propagation delay of the combination logic, and then the setup or the T setup of the second flip-flop, or the second register. So if I'm actually to take a look at this, this is usually the propagation clock to Q is given to us. It's actually right here, propagation clock to Q, and the setup time in here is also given to us. So these two numbers we have already. They're based on the flip-flops. We have no control over it. Usually we technically don't have control over TC, but in this particular example, we're just trying to figure out the maximum frequency that this particular circuit can actually operate at. If we're assuming that circuit, this is the only path, or these are the only paths within this circuit. It's actually one single path, because I have one register, and they're connected with a combination logic here. So what I really am asking is, what's the propagation delay? And the propagation delay, if you remember, this is the maximum delay you can get within the combination logic. And the way we can think about it is, we need to figure out what the critical path, let me call it the critical path, or the longest path for a signal to traverse. And I'm just going to highlight it. It's actually in here, and you can see that this particular path will lead to a signal traveling through three different gates. For example, let's assume that this B was 1 and this is 0. Really, like if you have this as a 1, this will change to 1. For example, if it was, let's assume that A was 0 and then you made it a 1. So this will become a 1. This will become a 1 in here. Of course, this will become a 1 after it was a 0. And then this will be a 1. And then it will be based on the value of D. Let's assume that D is actually 1. This will become a 0 in here. And it will change accordingly. So you'll have to pass through 1, 2, and 3. And the maximum delay for this one is actually the propagation delay and propagation delay and propagation delay. So this number, as it turns out, is easy to calculate. It's actually, it's 80 plus 3 times 40 plus 50. And that's actually the TC. And if you actually calculate that number, you're going to see that TC is greater than or equal to, I believe it's 250 picosecond. So that means the f of c, which is the frequency, is just must be less than or equal to 4 gigahertz. So the maximum frequency that I can actually use with this particular circuit is 4 gigahertz. If I use something that is 5 gigahertz or any number above 4 gigahertz, I will be violating the setup time constraint in here. So I can't do that. All right. Generally speaking, in a timing analysis, this is what you care about. You care about the maximum frequency you can operate at. But usually you also have to actually look at the hold time and make sure that it is actually not violated. So let's take a look at that in here. So I'm going to start by writing the setup time constraint inequality. I keep calling them equation. They're all inequalities here. So it tells me that the T hold has to be less than or equal to T contamination clock to Q plus T contamination delay. So I'm writing it down. I'm not memorizing any of these. I'm just copying them here so that we can see them. And again, all we have to do is just figure out, do we have this one here? I believe we have it. Let me just highlight it in a different color. Okay, so we have it in here. So we have that contamination clock to Q is here. This is the contamination clock to Q. Do I have the T hold? Yes, I do have the T hold. It's right here. However, I don't have the contamination delay because it depends on this particular combination logic. And what's the contamination delay? It's the shortest amount of time that you would need for a signal to start in this part and actually ends in this part in here. Remember, this is the whole combination logic. And really, this is easy to figure out. You can either think about it this one or this one. It's just a single gate. So the contamination delay for the combination logic is just a single gate. And we have that number. It's actually this one in here. All right, so all we have to do is just substitute these numbers, and we're thinking about 60. Is it less than or equal to 30 plus 25? And the answer is 60 is definitely not less than or equal to 55. What this tells me is, since it's not, that means the whole time constraint is being violated, and this circuit will result in a metastable condition because of that. All right, so again, usually you will see that whole time in here is less than the T contamination clock to Q. If it is less than that, let's assume it's less than 30. Let's say it's 20. There's no way that setup time will be or the whole time will be actually violated, because it will be always less than 3. Then plus, like, even 0, it will be actually it will be maintained. All right, so what's the solution if I actually figure out that the timing constraint, one of the timing constraint, has been violated? If it was the setup time that has been violated and I don't want to change the combination logic, I can think about, well, let me reduce the frequency that I'm operating at, and that's it. But for the whole time, the fix has to be by adding something to the combination logic. This is why maintaining a hold time or a T hold that is less than the T contamination clock to Q is usually crucial, because if you make a mistake in the design and you come back to fix it, you'll figure out that actually the only way to fix it is to modify this particular circuit. There's no other way around it. You can't just change the frequency you're operating at and say, hey, that's it, like I made a mistake, let's do that. So how do we fix it? Well, the solution is actually to add certain delays. As it turns out that the signal is too fast, it's generating the signal too fast. I'm just going to make sure it's delayed. And the way we can do it is just by adding a couple of buffers on these like paths. So I've showed you that this path actually was at least the shortest path, or the path that is giving me these contamination delays. And this is the same. It's actually one gate. So what I'm doing in here is I'm just adding another gate. So let's see if that T hold is actually here. So the equation was this one here. Let me just copy them, or do this here. I'm going to copy that, and I'm going to show you how this changed. So now I'm going to write the change in red. So now I have the T hold is still 60. Nothing changed in here. The contamination delay is still 30. Now what changed is the following. What changes now, I have two gates, so it's actually 25 times 2. So that means 60, is it less than or equal to 80? And the answer is yes, and now the whole time has been corrected. So the correction was to change the combination logic. Now, of course, after you change the combination logic, you're going to have to make sure that your maximum frequency didn't get added. Like, for example, if you add a buffer in here, you will be adding a delay that is not necessary, for correcting anything. But let's take a look in here. I think still this here is actually the critical path for the propagation delay. So nothing has changed. So the setup time constraint analysis is still the same.